Hello everyone, welcome to Digital Communication Tutorials. In this video, I am going to discuss the sampling theorem. Please note, this is also called as ideal sampling theorem or sampling for low pass signals or sampling for band limited signals. Let us start by considering an analog signal g of t that is continuous in both time as well as amplitude. Further, we will assume that the signal g of t has infinite duration but finite energy. Then we are going to extract the sample values of the signal g of t at times t given by 0 plus or minus ts plus or minus 2ts etc. and let the samples thus generated be denoted by the series given as g of nts, where n takes on the value 0 plus or minus 1 plus or minus 2 etc. Here we will refer Ts as the sampling period and Fs equals 1 by Ts as the sampling rate or the sampling frequency. Now let us have a look at a segment of the signal g of t we have considered as input. This in fact is what is g of t represents, and this is actually the sampled signal which is taken or which is constructed by instantaneously sampling the input signal g of t by taking on the amplitudes of g of t at regular intervals given by Ts. So, the discrete time signal g delta of t that results from such sampling process can be represented by an equation as g delta of t equals summation n varying from minus infinity to plus infinity g of nts into delta of t minus nts. Here what is very important is the delta function, and here this is called as the Dirac delta function, which is located at t is equals to nts. Now for n is equals to 0, we have a diagram for the Dirac delta function given by this. So this in fact is the Dirac delta function given at n is equals to 0. Coming back to the equation 1, we note that each delta function in the series generated is weighed by a corresponding sample value of the input signal g of t, and this sample value is given by g of nts. This in fact is what is represented by figure 1.b, which is our discrete time signal generated by sampling g of t by using instantaneous sampling technique. Coming back to the equation 1, we note that by the definition of the delta function we can write g of nts into delta of t minus nts equals g of t into delta of t minus nts. So, we will now rewrite equation 1 by substituting this part by this part to generate a new equation given by g delta of t equals g of t into summation n varying from minus infinity to plus infinity delta of t minus nts. Here delta ts of t is the Dirac-Coombe function, which is also called as the ideal sampling function. We in fact have a diagram for that also. This is the Dirac-Coombe function. If you compare these two, you will note that a Dirac-Coombe function is simply a shifted plus added version of the Dirac delta function at regular intervals. Coming back to equation 2, we may view the discrete time signal g delta of t generated by the instantaneous sampling as the output of an impulse modulator, which operates with g of t as the modulating wave and delta ts of t as the carrier wave. In fact, we can build a simple circuit theoretic interpretation of g delta of t using the diagram that is shown here. So, we have an impulse modulator, the input to which is our modulating wave given by g of t, and the impulse modulator works with a carrier wave represented by delta ts of t, and the output of this impulse modulator is our instantaneously sampled wave represented by g delta of t. Now let us come back and discuss equation 2 in a little bit of detail. From the properties of the Fourier transform, we know that the multiplication of two time functions is equivalent to the convolution of the respective Fourier transforms. So let g of f represent the Fourier transform of g of t and g delta of f represent the Fourier transform of g delta of t. Now, if I apply Fourier transform to equation 2, I would require the Fourier transform of delta Ts of t, and this in fact is given by f of, which is the Fourier transform of delta Ts of t, equals Fs multiplied by summation m varying from minus infinity to plus infinity delta of f minus mfs. Here Fs in fact is the sampling rate. So, now I am going to apply Fourier transform on equation 2 and transform this time domain signal into a frequency domain signal to obtain g delta of f equals g of f convolution. This in fact is the Fourier transform of delta Ts of t as given by equation 3. So, I am going to substitute the RHS of equation 3 here. Now, let us interchange the orders of summation and convolution to get Fs and summation outside. Then we have g of f convolution delta of f minus mfs. Further, from the properties of the delta function, we find that the convolution of g of f and delta of f minus mfs equals g of f minus mfs. So, I will modify equation 5 by substituting the convolution term by g of f minus mfs. Now, from equation 6, we see that g delta of f, which is the spectrum of the sample signal, represents a spectrum that is periodic in frequency f with a period fs, because you can see we have f minus mfs. That means g of f is repeated after each fs. However, we should note that this is not necessarily continuous in nature. In other words, the process of uniformly sampling a signal in the time domain results in a periodic spectrum in the frequency domain with a period equal to the sampling rate, which is here represented by Fs. Therefore, g delta of f represents a periodic extension of the original signal g of f. Now, let us go back and look at equation once again. We can obtain another useful expression for the Fourier transform of g delta of f by taking the Fourier transform on both sides of equation 1 and noting that the Fourier transform of the delta function, which is delta of t minus nts, is given by Fourier transform on delta of t minus nts equals exponential of minus j 2 pi n f ts. So, now I am going to apply Fourier transform on equation 1 and substitute the delta of t minus nts term by exponential of minus j 2 pi n fsts, and this will create this equation, which is equation 7, which is g delta of f equals summation n varying from minus infinity to plus infinity g nts into exponential of minus j 2 pi n fts. It should be noted that we have retained g of nts as it is because it is a sample and can be considered as a constant. Then equation 7 can be viewed as a complex Fourier series representation of the periodic frequency function g delta of f with the sequence of samples given by g of nts defined as the coefficients of this particular expansion. Please note, all the equations we have derived till now, that is from equation 1 till equation 7, can be applied to any continuous time signal g of t of finite energy and infinite duration. Now, let us consider that the signal g of t, which is our input signal, is strictly band limited with no frequency components higher than w hertz, where w itself can be considered as the highest frequency component of g of t. So, the Fourier transform of the original signal g of t, which is represented by g of f, has a property that g of f is 0 for frequencies greater than or equals to w. This is shown by the figure 1 here, which is in fact figure 5a. What we are supposed to note here is that we have the spectrum of our input signal represented by g of f, which is very strictly band limited. That is, there are no frequency components which are greater than w. Now, let us consider this particular signal, which is our strictly band limited signal g of t, is sampled by using the sampling period Ts equals to 1 by 2w. That is, let us simply choose the sampling period to be 1 by 2w. So, I am going to substitute Ts equals to 1 by 2w in my previous equation, which is equation 7 here, and this is going to create a new equation given by g delta of f equals summation n varying from minus infinity to plus infinity g of n by 2w, because previously it was nts, and since ts is equals to 1 by 2w, it is g of n by 2w multiplied by exponential of, previously we had minus j 2 n pi f ts, but since ts is equals to 2w, we will cancel the 2 here in the numerator and denominator to get a simplified expression as exponential of minus j n pi f divided by w. Further, let us substitute fs, which is our sampling rate, equals to 2w into equation 6. So, I am going to substitute fs is equals to 2w, and I am going to rearrange this equation to get a new equation which is given by g of f equals 1 by 2w into g delta of f. Now, since our g of t is very strictly band limited, I must put the limits of frequency as minus w less than f less than plus w. This is necessary because now we have assumed our input signal g of t to be very strictly band limited. Now, you can see equation 9 RHS is g delta of f. Now, I will substitute the RHS of equation 8, which in fact represents g delta of f, into the RHS of equation 9. This will give a new equation which is written here, that is g of f equals to 1 by 2w summation n varying from minus infinity to plus infinity g of n by 2w, which is our sample, multiplied by exponential of minus j n pi f divided by w. This is once again for frequencies between the limits minus w to plus w. Now, from equation 10, we should note, if the sample values g of n by 2w of our input signal g of t are specified for all time t varying from minus infinity to plus infinity, then the Fourier transform g of f of our original signal is uniquely determined by using the Fourier series equation that is given by equation 10 here. In simple words, if the sampling is taken, or if the sampling is performed in such a manner that we generate a sample for each and every value of t, then the Fourier transform g of f of the signal g of t is uniquely determined by using the expression as shown in equation 10 here. Since g of t is related to g of f by inverse Fourier transform, it therefore also follows that the signal g of t is itself uniquely determined by the sample values which are given by g of n by 2w, where n takes on the value anything between minus infinity to plus infinity. In simple words, the sequence g of n by 2w that is generated by instantaneous sampling contains all of the information of the original signal g of t. This is what is the overall idea behind the sampling principle. Now, let us move on to the reconstruction part. Here, we are going to reconstruct the original signal g of t from the sequence of samples that are generated at the end of sampling, and these sequence of samples are represented by g of n by 2w. So, what I am going to do is substitute equation 10 in the formula for inverse Fourier transform, which defines g of t as given by this equation, that is g of t equals integral minus infinity to plus infinity g of f into exponential of plus j 2 pi f t df. Now, let us take g of f from equation 10 and substitute to create a new equation. We should in fact note that since the limits of this frequency component is between minus w to plus w, the limits of the integration will also change to minus w to plus w. So, the equation becomes g of t equals integral minus w to plus w 1 by 2w summation n varying from minus infinity to plus infinity g of n by 2w, which is our sample, multiplied by exponential of minus j n pi f divided by w. And please note, this exponential term is taken from the equation 10. Then we have the exponential term which is from the inverse Fourier transform equation retained as it is here. Now, let us interchange the order of summation and integration to obtain. Let us take the summation and g of n by 2w outside. Then we have 1 by 2w. Then we have integration between the limits minus w to plus w, exponential of here I am going to simplify this by taking some common terms which are j 2 pi f. So, exponential of j 2 pi f multiplied by t minus of n by 2w df. The simplification of this equation is quite complex unless you know the integral term in equation 11. However, we have a ready equation that defines the integral term, and this is given by, this you please note is the integral term in equation 11 here, and this is equal to 2w into sine of 2 pi wt minus n pi whole divided by 2 pi wt minus n pi. So, I am going to substitute the RHS of this equation in place of the integral term in equation 11 to obtain a new equation which is g of t equals summation n varying from minus infinity to plus infinity g of n by 2w multiplied by, in place of the integral term we will write this. Now, here what is written here is 2w multiplied by sine of 2 pi wt. In the equation 11 you should note there is already a 1 by 2w term. So, we will cancel out 1 by 2w and the 2w here, and that is why equation 12 does not have the 2w term involved. Further, the equation 12 that is generated by substituting the integral term by the sine term can be simplified by using the sinc function, which is of the form sinc of x equals sine of pi into x divided by pi into x, where x can be an independent variable. So, since we have sine of 2 pi wt minus n pi, I can take pi as common. So, whatever remains, let it be taken as x. The same can be done in the denominator also. If I take pi common, whatever remains can be treated as x. Further, what is also interesting about the sinc function is that it exhibits an important property called as the interpolatory property. And this property is given by the equation here, that is sinc of x equals 1 when x equals 0, and otherwise the value of sinc of x is 0. This in fact is shown by the diagram here. You can see when x is equals to 0, that is here the x axis is t. So, when t is equals to 0, sinc of t is 1, and for every integer multiple value of t, that is plus or minus 1, plus or minus 2, etc., the value of sinc of x is 0. So, this is what in fact is depicted in equation 14 here. So, I am going to now use the sinc property and substitute the term that is given here, that is sine of pi into x divided by pi into x as sinc of x. Here you should note x equals to 2wt minus n. In fact, that is what is written here. So, g of t therefore can be written as summation n varying from minus infinity to plus infinity g of n by 2w multiplied by sinc of 2wt minus n. Now, the equation 15 that we have obtained here provides an interpolation formula for reconstructing the original signal g of t from the sequence of samples generated by instantaneous sampling, which are also represented by g of n by 2w. However, the most important thing about this equation is that the sinc function, that is sinc of 2wt minus n, itself will act or play the role of an interpolation function. So, each sample is multiplied by a delayed version of the interpolation function, which is our sinc function, and all the resulting waveforms of this multiplication are added to obtain the g of t. That is why there is a summation term here. It is also worth noting that equation 15 represents the response of an ideal low pass filter of bandwidth capital W and 0 transmission delay, which in fact is produced by an input signal consisting of a sequence of samples given by g of n by 2w. Here n can take, once again as previously discussed, any value between minus infinity to plus infinity. Further, from this diagram we note that the original signal, which was between the frequencies minus w to plus w, in fact still exists between minus w to plus w in the sampled signal also. However, since when we were discussing the sampling procedure, let me go back to that equation, right. So, this is our equation. From equation here we note that the spectra of the sample signal is replicated by a value of fs. So, what we are seeing here is a replica of the original frequencies being generated at a certain interval given by fs, because fs is our sampling rate. It is also worth noting from our previous expression, that is equation 6, the spectra in fact is now multiplied. I simply weighed by the term Fs. Now here Fs is equals to 2W. Therefore, when I go to the spectra of the sample signal, you will see we have a 2W multiplication factor in the amplitude of the sample signal. Now, since we are talking about reconstruction, what we are interested from the sample signal is quite obviously those frequencies that lie only between minus W to plus W, because these are our original frequency contents. Any other frequencies in the sample signal spectra can simply be regarded as the replica of the original signal and therefore can be eliminated during reconstruction. This in fact can be done by passing our sample signal G delta of t through an ideal low pass filter of bandwidth W, because that is what is the limitation of our original signal. So, this is what is being shown in the diagram 3 here. As per the discussion, if our reconstruction filter is limited only between minus W to plus W, then by passing G delta of t through such a filter will only retain frequencies between minus W to plus W. Additionally, it is also important to note that since the sampling procedure has changed the amplitude of the sample signal by the factor 2W, the reconstruction filter amplitude response is given by 1 by 2W. So, we will have these factors cancelled and therefore, we will obtain the amplitude of the original signal as it is. This overall operation of reconstruction can be simply shown using a block diagrammatic format as shown in the figure here. That is, at the input of the reconstruction filter, we have a sequence of samples given by G of nTs, where Ts is equals to 1 by 2W. When this sequence of samples is passed through our ideal low pass reconstruction filter, we are going to obtain in an ideal sense our original analog signal G of t. Right. So, that is about both sampling as well as reconstruction of the band limited or low pass signals. In simple words, you must remember this is an ideal sampling theorem and does not take into effect the practical aspects of sampling. Further, we have assumed that our input signal G of t is continuous in both time and amplitude, as well as it has infinite duration and finite energy. So, these factors and these assumptions will be tested when we take the practical aspects of sampling in one of my future videos. So, to conclude, let us state the overall sampling theorem, and in fact, the sampling theorem for band limited signals can be defined in two parts. The first part is for sampling, the second part is for reconstruction. So, let us read the first part, which is for the sampling. If a finite energy signal contains no frequencies higher than W hertz, we already have said W is the highest frequency content of the input signal, then such a signal is completely determined by specifying its ordinates. Ordinates are nothing but samples. By specifying its ordinates or samples at a sequence of points spaced 1 divided by 2W seconds apart. So, this part simply states that if the sampling is done by taking samples with having a separation between each sample equal to 1 by 2W, then the sampling can be done successfully. That is about sampling. Coming to the reconstruction, we once again start by the same sentence, that is, if a finite energy signal G of t contains no frequencies higher than W hertz, then it may be completely recovered. Please note, completely recovered from its ordinates, which are nothing but samples, which are then supposed to be placed at a sequence of points spaced 1 by 2W seconds apart. So, this is what is the overall definition and statement of sampling theorem. Before I conclude, there are some very interesting observations you must make. The first two observations can be considered as the statement of the sampling theorem itself. Additionally, while we were trying to perform sampling, we noted that Fs is equals to 2W. This can be taken as and most commonly referred to as the Nyquist criteria. That is, when Fs is equal to 2 times the highest frequency content of the input signal, then sampling at such a rate can be considered as the Nyquist rate. We also have two more conditions. The other conditions obviously will remove that equal symbol between Fs and 2W. Thereby, we create two more extras. That is, when the value of Fs, that is our sampling rate, is greater than 2W, which in fact is one of the most practical scenarios, then such a type of sampling is called as oversampling. On the other hand, if the sampling rate, which is Fs, is less than 2W, then this is called as undersampling. This in fact is correct because when I was showing the diagram for the sample signal spectra, you see the replicas of the spectra touch each other, but they do not either overlap nor create any gaps in between them. So, here Fs equals 2W is applied. Now, when I take, as I am showing in the diagram here, Fs greater than 2W, then there will be gaps created in between the spectra. On the other hand, when Fs is less than 2W, we will see the spectra overlaps each other, and this is called as aliasing. Yeah, we have now come to the end of this session on the ideal sampling theorem. If you like this video, kindly press that like button and subscribe to my channel. Thank you for watching. Have a good day.